For the problem of the day that I gave you, I tried to give you a hint where I said that the product of this reaction has a retention of configuration. The other key thing that you may have noticed was that I only gave you one product. I didn't give you a mixture of stereoisomers. What sort of reaction does this give you a hint as to? SN2. If it were SN1, we would get a mixture of stereoisomers, right? So we immediately have a strong hint that this has got to be an SN2 reaction. The problem I see is that an SN2 reaction normally has an inversion of stereochemistry. This one, we've got a retention of stereochemistry. How can we solve this problem? Do it twice, right? If you flip something inside out and then flip it inside out again, you're back to where you started, right? There is recent literature from a group at UC Berkeley where they can do substitution reactions in one pot and get a retention of stereochemistry, but it's really difficult and requires exotic catalysts and still doesn't work with very many electrophiles. So for the most part, if you want to retain stereochemistry, you have to do two different SN2 reactions. All right, so let's get started. Can I just react this with a nucleophile and have our hydroxide act as a leaving group? No, hydroxide's a terrible leaving group. It's not going to fall off. So what can we do to change that hydroxide or alcohol into a good leaving group? Yeah, we can tosylate it. So I'm going to abbreviate this as tosyl chloride, TSCl, and pyridine. And if you noticed, I didn't change the stereochemistry at all. Why is that? Yeah, we didn't do a substitution, right? That carbon where the stereo center is at was untouched during this whole reaction. Nothing happened there. All we did was we changed that alcohol into a much better leaving group. Okay. What should I use for my first SN1 reaction? What nucleophile? Anybody want to throw out a suggestion? I heard sodium iodide the loudest, so I'll put that down. So we've got Na, I minus. What sort of solvent should we use? So DMSO, acetone, something that's polar aprotic, right? So let's maybe just throw down acetone. All right, and then we're going to do our backside attack. It's going to kick off our leaving group. We're going to get our inversion of stereochemistry, and we're going to get OTS minus as our leaving group, and our sodium as our spectator ion. What nucleophile should I use in my second step? What was that? NaSH, NASH. All right, if we have this go in and attack, this will again do a backside attack, kick off our iodide, and we get to our final product. Oops. Plus sodium iodide. Now, Grace asked me this weekend a good question. She was asking, why don't we just throw in a strong acid in this case and do the protonation, turn it into water? Water is a good leaving group. Does anybody know why? Yeah, so let's take a look at if we tried to do this with acid. I'm going to protonate it and just say, all right, this alcohol is going to come grab this proton. We've got OH2 plus. This water can fall off and go through an SN1 type reaction, giving us this secondary carbocation. Secondary carbocations are quite unstable, at least compared to tertiary. Is there any sort of rearrangement we can do to stabilize this?
Double bond.
What's that?
The double bond resonance.
Oh, there's no resonance. Because remember, we've got two hydrogens coming off here. So we can't move that double bond without forming a Texas carbon. Yeah, but what we can do is do a hydride shift. And if we did this, we could get a secondary carbocation, but why is this secondary carbocation much more stable? It's allylic. It's secondary. It's got resonance now. So this is a really stable carbocation. And then if we tried to react this with some sort of nucleophile, actually, let me redraw this a little bit. Shoot. If we tried to react this with some sort of nucleophile, we would end up with a mixture of products, both of which have the wrong regiochemistry. So in class, I told you guys that normally we do tosylation with SN2 and protonation with SN1. This is the reason. If we do protonation, oftentimes it'll go through an SN1 type mechanism and you get uncontrollable rearrangements occurring. If you do tosylation, you're stuck doing exclusively an SN2 mechanism and you don't observe any rearrangement reactions. That's not to say that you won't see protonation occur with an SN2 type reaction, but you only see it on primary carbons, not secondary carbons where you would potentially see an SN1 type mechanism. So it is a little tricky, but like I said, tosylation is preferred for SN2, protonation is preferred for SN1. Always something to watch out for. All right, are there any questions before we move on? One thing I did want to say was I went on Sapling this morning and I saw a good half of the class is still not done with Chapter 7. Make sure you guys get that done quickly. Chapter 8 is going to throw a whole new wrench into this situation, and I want to make sure we're all up to speed. So let's move on to Chapter 8. Chapter 8 is all about alkenes. So let's start with the basics. We're going to do alkene nomenclature. Alkene nomenclature is pretty straightforward. It's similar to the nomenclature for alkanes. So what's the first step when we're naming an alkane? What do we want to identify? The longest chain, right? So identify your longest chain. Number 2 is identify your substituents coming off of that chain. Number 3 is number so that your double bond is at the lowest number. When we were naming alkanes, I said that we want to number it to minimize numbering. With alkenes, the rules are different. With alkenes, our main goal is to make sure that our double bond has the lowest numbering. That's the trump card here. Number 4 is we still want to alphabetize substituents. And then last but not least, we're going to end with a prefix where you've got a number dash dot 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 ene. So we do need to include the alkene ene suffix, not the ane suffix that we saw with alkanes. And I'll show you how we'll piece this together using some example problems. So let's do an easy example first. Let me clean this up. What's this compound called? What's the longest chain? 6. So what's the prefix for 6? Hex. Do we want a number going left to right or right to left? Left to right. That way our double bond starts at position 2, goes through 4, 5, 6. All right, so we've got a hexene. And is this cis or trans? Trans. If we think about the hydrogen coming off of position 2 and the hydrogen coming off of position 3, they're on opposite sides. So this would be trans. So we can go through and we can say, all right, this is trans 2, indicating our double bond starts at position 2. Hexene. So the 2 simply indicates that position for a double bond. Let's do another one. Oh, here we go. There we go. That looks better. Let's try naming this one. What's our longest chain? 7. 1, 2, 3, 4, 5, 6, 7. All right. And do we want a number going right to left or left to right? Yep, we want to go left to right. So we go 1, 2, 3, 4, 5, 6, 7. That way the double bond starts at position 3, not position 4. All right. Is this cis or trans? Think about the hydrogens coming off of 3 and 4. Are they on the same side or opposite side of the double bond? Opposite. Remember, if you guys are forgetting some of our cis and trans rules, we can draw this imaginary line going through. We can say there's a hydrogen here, there's a hydrogen here. They're on opposite sides, so they'd be trans. So again, we can go through and we can say, all right, this is trans. And then what should we name our substituents? Yeah, it would be 2, 5, 5 trimethyl. And then what's the suffix going to be? It's going to be a heptene, but we have to include a number to indicate where the double bond's at, right? So it'd be 3 heptene. One thing you will see occasionally is people writing this using slightly different nomenclature. So another acceptable way of writing this first one would be trans hex 2-ene. So they put the 2 in front of the E and E to indicate that's where the double bond's at. IUPAC rules say that's perfectly allowed. You can draw it either way or write it either way. Same with this one. We can say trans 2, 5, 5 trimethyl hept 3-ene. Some people prefer to do it this way just to clearly indicate that the double bond is located at the 3 position. Yep.
Do we have to always mention whether or not it's cis or trans?
You should try to, yes, because it does have a big impact, right? Just like if you guys go to the store and you see a food label that says full of trans fats, you're going to be a little skeptical of that, right? Cis and trans has very, very different properties, and we do need to designate it. All right, let's do a couple challenge problems, and I want you guys to work on this. I'm going to pull some...
Can we have some size examples?
Some what?
Can we have some size examples?
Some size examples?
Cis, sorry.
Oh, some cis examples? Well, we'll go through and do some of these first. Let's try this one. Oh, tricky, tricky. And then a second one over here. You guys remember how to name bicyclic rings, right? You didn't forget that. At least I hope not. So let's name both of these. Everyone's size. Let's look at the bicyclic one. Where do we start numbering when we're numbering a bicyclic ring system? Bridgehead, right? All right, so I'm going to number here. Do I go 1, 2, 3? No, the other way. Why do I go the other way? Yeah, minimize the double bond numbering. So we go 1, 2, 3, 4. And then do I go 5? No, we go around the ring that's biggest. So 6. And then 7. Okay. So we're getting there. Right now, what we have is an alkene, but is it cis or is it trans? It's cis, but is there the option of making a trans one here? Not really easily, but we can label it cis just to indicate that, and I'll talk about that here in a second. So this is cis 2,3-dimethyl. And then what goes next if it's a bicyclic ring system? Bicyclo. Whoops. Bicyclo. And then we put in our brackets here. What should go in our brackets? 2, 2, 1. And then we've got hept, because we've got a total number of 7 carbons in our ring system. We don't include our substituents because they're not a part of the ring system. And then our double bond comes off carbon 2, so I'll do hep2-ene. That's a mouthful.
Can you explain why it's cis?
Because if you look at the methyl groups coming off of 2 and 3, they're coming off that same side. So we would call it cis because of that. Going back to naming rings with double bonds in them, typically you don't see trans double bonds in rings unless you're in a ring size greater than 8. Why is that? Yeah. If, for example, I'm just going to scroll down. For the sake of argument, let's imagine trying to draw a trans cyclohexene. Can you guys draw that very easily? Well, let's try. Let's see, I've got 1, 2, 3, 4, 5, 6. Does that look like a very happy molecule? No. It's really, really hard to draw trans double bonds in ring systems unless you're getting into really, really big ring systems like a cyclooctane or a cyclononane, or nonene, I should say. So always be aware of that. Sometimes you won't see cis and trans written for ring systems unless you're dealing with really, really huge rings. All right, let's do the next example. Let's try to name this one. Yep.
When we're numbering a ring with double bond, the alkene in it, does it matter if we say, we have to say one like hexene, because again, it doesn't assume that we'll start at the double bond going on the ring, or do we have to number that?
You always want to start at the bridgehead. So the one position will always be at a bridgehead when you're numbering a bicyclic ring system.
Well, what about a one ring system? Just a ring, not a bicyclic.
Oh yeah, let's say you're talking about cyclohexene like we made in lab.
Yeah.
You don't have to say one because it's implied, right? So if you are running into situations like that, you don't have to necessarily number them. Same with cyclohexanol. The alcohol is always going to be coming off the one position because you choose how to number it, right? Yeah? Okay. Yeah?
What's the 221 mean?
So the 221's in reference to our bridge lengths, right? So if we look at the bridgehead, we've got 1 and 4. Those are our bridgeheads. The path length is 2 carbons going one direction, 2 going the other, and 1 going the last. So let's name this last compound, and then we'll move on. What's our longest chain?
7.
Okay, 7. Where do we start numbering? Up on the top. We could go 1, 2, 3, 4, 5, 6, 7. Why didn't I number this going 1, 2, 3, 4, 5, 6, 7? Yeah, the double bond has to be in the parent. If it's not in the parent, you're going to run into problems. So by using our red numbering, it works out. Why didn't I go ahead and say 1 over here? Because it doesn't matter, right? So in this case, we're not overly concerned with this. Doesn't really matter. Let's go ahead and name this. We've got some substituents coming off of here. So we've got this group. What's that called? Isopropyl. What's this one? Methyl. We've got an ethyl. And then a methyl. Okay, so now if we go ahead and we name this, what substituent should come off, or should be listed first with alphabetization? ethyl. So we go 4-ethyl. And then what goes next? The isopropyls or the dimethyls? Isopropyl, because I beats M. So this would be 3-isopropyl. Whoops. And then we've got a 2,5-dimethyl. And then 2-heptene. All right? Yep.
So if our parent chain were like only 6, would you still include the double bond even if there's like a possible chain that's longer? Does that make sense?
Yeah, you want to identify the longest parent chain that includes the double bond. Yeah, that's a good question. All right, is this cis or trans? It's neither, right? All right, then we have to use a different sort of naming system. So let's review this a little bit. E versus Z. And then we'll go back and we'll add in our correct naming for this top one. But let's review this first, because I know some people are a little rusty on this. Hold on a second. I had some examples written down. Here we go. Number 1 is assign first and second priority for substituents coming off each carbon. Meaning each carbon in the double bond. Number 2 says if highest priorities are on the same side, is it going to be E or Z? Z. Z same side, right? And then if our highest priorities are on opposite sides, it's going to be E. So we can use an alternate naming system besides cis and trans for these. So let's go through an example, and then we'll go back and name that last compound we were working on.
Can you refresh us on what E means?
So E is German for, oh man, I'm going to butcher this, Enthagen? Is that right? You don't know? I thought you were a German major.
It's a long time ago.
It was long. E is German for Enthagen, which means together. Z is, I think, zusammen, which means opposite in German. All of the early organic chemistry was done in Germany around World War I and World War II, and so they got to name everything. Yeah. All right. Let's try to figure out whether or not this one is E or Z. Well, let's go through and kind of break this apart. What's that?
But on the last problem, the priorities are like the same. It's 2 identical methyl groups off of the carbon bonds, right?
Well, let's go through and do this E through Z example, and then we'll go back and look at that first one. All right, so we cut that double bond with an imaginary line. Now what we have to do is look at the first carbon. So what I'm going to do is look at this carbon. So the substituent coming off here is attached to 3 carbons. So we'd say C, 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 right? And then over here, what's that substituent attached to? CCH. So it's attached to 2 carbons and a hydrogen. Which one's going to be higher priority? The bottom one, the tert-butyl group, that CCC. So we'll name this 1, we'll name this 2. And then if we go through, we can say, all right, if we look up here, what's attached to that carbon? HHH. And then if we look down here, what about this one? Yeah, CCH. So which one's going to be a higher priority? The one on the methyl group or the cyclohexane ring? Cyclohexane. So if we look at this, we could label these 1 and 2. The 1s are on the same side. So what would this be? Z. Okay, so let's go back and look at our example that we left behind. And let's try to assign priorities to this one. This one's a little trickier. I'm going to erase some of this off of here, just to give us more room. But we're going to have to deal with a lot of tiebreakers here. All right, so if we look at this carbon up here, we've got a HHH. And then this carbon over here is also going to be an HHH. So if we think about this, are our lowest priorities going to be on the same side, opposite sides, or neither? Neither. So could we really assign this as E or Z? No. If we tried to even flip it, we'd be stuck, which is what Sarah was saying, but I didn't want to give away the secret quite yet. Sorry about that. So there are some situations where you can't designate it as E or Z because it is neither. All right, does that make sense, or do we want to go through and do a couple more? Couple more? All right, let's do one more, practice one. Let's do this one. So what's our longest chain here? Longest chain is going to be 9. So we can go through and we can say 1, 2, 3, 4, 5, 6, 7, 8, 9. That longest chain needs to include that double bond. And then we want to go through and we want to label our substituents. We've got a fluoro. We've got a methyl. We've got a methyl. And we've got a methyl. All right, is this an E or a Z alkene? So let's go through and just for the sake of argument, work through this. Again, we'll put our double bond through here. What's higher, fluorine or a carbon? Fluorine. So we'll label fluorine as 1. We'll label this one as 2. And then what's going to be higher for the bottom carbon, the right-hand side or the left-hand side? Right-hand side, because this one is attached to, the one on the left, I should say, is attached to 3 hydrogens. The one on the right is attached to 2 hydrogens and a carbon. So we can label this as 1 and 2. So this would be Z. So we've got Z, 3 fluoro. Let's see, 2, 4, 7 trimethyl. 3 nonene. And there we go. So you can get into a lot of these. We're going to go through a bunch of nomenclature, but there will be nomenclature on the next exam as it pertains to alkenes. So make sure that you guys are comfortable with that. Yep.
Can it be on the same side, like instead of top and bottom, can it be on the same side?
Are you saying what if we have 2 fluorines coming off of 1 carbon?
Yeah.
If you did that, you could make that molecule, but you couldn't identify it as cis or trans. Because
So it has to
you'd
be-
have equal priorities on both sides, so you have to have a difference of priority off of each carbon.
Okay.
Yep.
What if you have a ring with a double bond that has like a substituent coming off of one side of the double bond? How do you prioritize that?
So are you talking about like a cyclohexene with a...
Yeah, like cyclohexane with like a methyl group attached to like one of the double bonds. Does that not work?
So are you saying... I'll try to draw an example. Something like that?
Yeah.
Okay, let's try to name this one. Where would our number 1 start? It would have to start up here, right? Because that would minimize numbering and still put the double bond in the lowest priority. So there'd be 1, 2, 3, 4, 5, 6. So if we named this, this would be 1 methyl, 1 cyclohexene. Why didn't I say cis or trans here? Because with small rings, it's always going to be cis, right? We're never really going to run into trans. And well, I should say, why didn't I say E or Z? In this case, it's always implied that it's going to be Z for a small ring because of the small ring system. If we had a larger ring, we could run into E and Z. Yep.
What if you have 2 double bonds in a strand?
We're going to leave that for right now. We're going to get into conjugated systems, but those are called dienes or polyenes, and they have different naming systems. We'll cover that next term. Yep.
Can you explain the naming of the cyclohexanol?
Naming of cyclohexanol. Well, it's an alcohol, so the suffix changes to OL, and we'll talk about alcohol naming when we get to that chapter.
Okay.
Yeah.
I mean, we got that one there, so.
Well, this is a cyclohexene, not a cyclohexanol, like we saw in lab. Yeah.
I was just curious, what if your double bond is a substituent?
You always want it to be included in the parent chain. If you get into really, really complicated naming systems, there's a whole list of rules. We're going to stick with really, really basic naming, and you want that double bond to be in the parent ring. Yeah. All right, so let's continue on and talk about alkene stability. So we've got a bunch of different types of alkenes. We can have this alkene, we can have this alkene, we can have our trans alkene. We've got this alkene, and we've got that one. These are all the different possible conformations of alkenes, right? What's the difference between them? Yeah, the number of hydrogens or the number of substituents coming off of them, right? So if we look at this, what we call the one on the far left is we call this monosubstituted. These ones are called disubstituted because they've got 2 different groups coming off of the double bond. This one is trisubstituted. And this one is tetrasubstituted. Those groups coming off could be anything. They could be methyl groups, ethyl groups, other sorts of functional groups. But the key is they're not hydrogens, right? Yep.
Substituted?
Yeah, so substituted, meaning if we look at this plain alkene, it's got a group coming off here and here. So 2 of them means it's a di. We're just counting the number of groups coming off of that carbon-carbon double bond.
So the sub could be named anything?
Yeah, we're just using general terms to describe these. Which one do you think is the most stable? So somebody said tetra. Why do you think tetra?
It's not substituted.
It's the most substituted. Yeah, we can relate this back to our carbocations, right? We said with carbocations, the more methyl groups you have around them, the more stability you get. Why was that? What was the special name for that phenomenon?
Hyperconjugation.
Hyperconjugation. Same thing is true here. So as we look at these, the more substitution we have equals increasing stability due to hyperconjugation. Do you have a question, sir?
Yeah, so I thought the hyperconjugation happened because you have like an empty p orbital being stabilized with molecular with a different p orbital, like a non-empty one? Is that something else?
That's a good question. So in this case, it's not an empty p orbital, but it is an adjacent p orbital. So hyperconjugation occurs when you've got a p orbital that's next door to an sp3 orbital. It's a really weak interaction between those two because they're not perfectly aligned, but it is still a reaction or a stabilization that can be measured. So it doesn't have to be an empty p orbital. It could be a full one.
Okay, but why doesn't like steric hindrance make this less stable?
That's a good question, and that's kind of leading into the next part. We can look at some of these and look at sterics because oftentimes we're running into a battle as chemists. We're comparing electronic effects and steric effects, and sometimes they don't always perfectly match one another. So the next thing I wanted to look at was trans versus cis, because they're both di-substituted. But which one do you think is going to be more stable and why? Trans. So if we look at the trans model, you see how the methyl groups are on opposite sides. These methyl groups are like helicopter blades. They spin around really rapidly, but they're on opposite faces of one another. That means they're out of each other's way. If we look at a cis alkene, we've got two helicopter blades that are almost like a Chinook helicopter. They're really close to one another, and they don't like being in that close proximity. So in this case, we can make a steric argument about the stability of alkenes, and we can say that trans alkenes are more stable due to sterics. So we've got these competing features. We have to look at electronics as one big feature, and we have to look at sterics as another big feature. All right, so let's talk a little bit about preparation of alkenes. This is where we're going to spend the bulk of the chapter, but I did want to introduce it today. We've got one method. So let's label this as method number 1. And let's say in method number 1, I've got a leaving group, and I've got a really, really strong base. Actually, let me even add on another group here. I'm going to add on 2 CH3 groups. There we go. So we've got a leaving group attached to a secondary carbon. What chemists do is we like to identify these carbons and name them. So the carbon that is directly attached to the leaving group is called alpha. It's the alpha carbon. It's the one where the leaving group's hanging off of. What do we call the carbon that's one further away? Beta. So those of you that speak Latin, or at least know Latin terms, can predict. What do you think the next one is after beta? Gamma. Yeah, it's a little bit weird, but chemists like to use the Greek alphabet to order how far away from a reactive center we are. So alpha is the direct attachment, beta is one further away. In this reaction, the base really likes to grab beta protons. So let's look at these beta protons. I've got 3 of them right here. This base will actually reach over, grab one of these beta protons, and when it grabs that proton, we have to break a sigma bond. And this sigma bond will actually clamp down like a set of dominoes and then kick off our leaving group.
Is this the SN2 reaction?
Nope.
Or is
So now we've got our conjugate acid, HB, and we've got an alkene. This is not a substitution reaction, right? We have not substituted the leaving group for a nucleophile. Instead, we've eliminated off our leaving group, and we're left with an alkene. So this is an elimination reaction. If we look at this reaction, it relies on a base reacting with beta protons. So let's label that. or it relies on the collision or reaction between two reagents. So if we try to write the rate equation, what would it be? Would it be first order, second order, third order?
First order. Because the living group limit.
So let's write our rate equation. So we've got rate equals some little k. The concentration of our starting material on the left matters a lot, right? So we'll call this k, or our concentration of our substrate. And the concentration of our base matters a lot. So is this first order or second order? Second order. So what we call this sort of reaction is an E2 reaction. The reason we call it an E2 reaction is if you look at it, the E stands for elimination. The 2 stands for second order. Does this sound familiar at all to you guys? Yeah. I told you guys this is really closely related to substitution chemistry, and a lot of the naming systems, in this case the E2, is similar as well. We're going to talk a little bit about how to predict or differentiate between a substitution and elimination reaction, but I did want to present this to you guys as just the basic overall mechanism. If we've got an E2 mechanism, what do you think our other method is? E1. So let's write down method 2. You guys love your eliminations, don't you? All right, let's do method 2. We've got our leaving group. Let's label our alpha and beta positions on our substrate. We've got alpha, which is where our leaving group's attached. We've got beta, beta, beta. And then in an E1 reaction, what do you think the first step's going to be? Leaving group falls off. Just like we saw with SN1 reactions, the leaving group can fall off. Form a carbocation plus our leaving group that's got a negative charge. So it forms a stable carbocation. Do you think the leaving group matters a lot? Yeah, just like with SN1 reaction, we said that leaving group falling off is the rate determining step. So it's the same for an E1 reaction. And the leaving group is good. And this is our rate limiting step. And then if we've got our base around, we still have to look at our alpha and beta positions. And we said that bases really like to go after beta protons. So this base will reach around here, grab one of these beta protons, clamp down, give us our double bond, plus HB, plus our leaving group with a negative charge. So in this case, what do you think our rate equation is going to be? Our rate is going to be our little k times the concentration of our substrate. And so we call this an E1 reaction because it's a first order elimination reaction. All right, we've got time for an example problem that I wanted you guys to think about. And I want you guys to help me with the arrow pushing for this. provide the mechanism. First one, we've got sodium hydroxide. We get here. Do you guys think this is going to be an E1 or an E2 reaction, and why? Well, let's think about this. I'm going to throw down a second alternative. Oops. Same starting material, but this time we're going to use water. And get to the same product. Let's think about it as it relates to SN1 versus SN2. An SN2 reaction requires a strong or a weak nucleophile? Strong. SN2 reaction requires a strong nucleophile. In this case, do you think an E2 reaction requires a strong base or a weak base? Strong base. So which one do you think is most likely going to be an E2, the top one or the bottom one? Top one. So if we look at this one, strong base favors an E2 reaction. Bottom one, we said it's a relatively weak base, so this would favor an E1 reaction, just like our SN1 reaction only needs a weak nucleophile. So if we look at the first reaction, what's that sodium hydroxide going to do?
It's gonna take one of the protons from the methyl group.
It's going to grab a proton. Which proton is it going to grab? It's going to have to grab a beta hydrogen, but if we look at our product, these beta hydrogens here and here didn't get formed into a double bond, which means we must have grabbed one of the beta protons coming off of here. And we're going to talk more about how to predict products as this week goes on, but in this case, our product gives us a clue as to what beta proton we're grabbing. So we've got sodium that's a positive charge, hydroxide that's negative. This hydroxide, we said, is going to clamp down, grab this proton, clamp down, do a domino effect, and kick off our chlorine. And then our final product is going to be sodium chloride plus water. If we think about the next one, we said it's an E1 mechanism. So the first step is going to be this chlorine falling off. Whoops. We'll form our stable or relatively stable tertiary carbocation. And then same thing. We're going to grab this beta proton that's hanging off here. Oops. Oops. And our water can act as a weak base, grab this proton, and we actually end up with hydronium as our product. So again, it's always a good idea to label your alpha and beta protons to make sure that you're not accidentally grabbing a proton that's not a beta proton. We're going to review this a lot this week, but try to get started on your problem of the day early. A couple of you guys were asking too about the lab reports. Lab reports aren't due until a week after your last lab, so you get an extra week for this cyclohexane lab to turn them in. All right, I'll see you guys tomorrow or in lab.